Here's the definition of an antiderivative. The antiderivative of a function f is a function capital F such that the derivative of capital F is little f. Now, here's where you've already worked, because I know reading this aloud and looking at it, it can sound very confusing. Here's where you've already worked with antiderivatives. F is the antiderivative of f prime. So if I gave you f prime and asked you questions about f, you are answering questions about the antiderivative of f prime. So the function that precedes the derivative. F prime is the antiderivative of f double prime. So it's literally working backwards. Instead of finding the derivative, you're finding the function before it. So we've already worked through an example very similar to the example I'm going to go through with you now. It just was worded not with antiderivatives, but it's the same relationships we've been talking about. So for example, the relationships between f and f prime exist between f and its antiderivative, capital F. So here we're given capital F. It's an antiderivative of the function lowercase f, whose graph is shown to the right. So this is the graph of f, meaning this is as if you are looking at the graph of the derivative. So this is the graph of capital F prime. So all of the questions you just worked on where you were given the graph of the derivative, that's like this question. So if this is capital F prime, you are then asked in A, where is capital F increasing or decreasing? So how do you find where f is increasing or decreasing if you're given the graph of the derivative? Where it's positive or negative. So where f is increasing, this would be where f is positive. Decreasing would be where f prime is negative. So based on the graph we have, the graph is positive everywhere we can see from 0 to infinity. In which case this means f would be increasing everywhere. So we can say f is increasing on 0 to infinity. It doesn't ask you to justify it, but just so you understand why, since capital F prime is positive on that interval. And actually, I could have stated, since capital F prime is positive, this means lowercase f is really positive, since we were given the graph of lowercase f. So just tying in, I'm thinking ahead to justifying with AP questions, tying in that you know lowercase f is the derivative of uppercase f. So then, any questions on A? The derivative is positive, the original function or the antiderivative is increasing. Derivative is negative, antiderivative is decreasing. Then we have, where is capital F concave up or concave down? So how would you be able to tell concavity if you have the graph of the derivative? And then, Emma, what are you saying? Yes, and when capital F prime or lowercase f, when it's increasing, the slopes would be positive, yes. So it is what both of you are saying, a combination. So capital F is going to be concave up. This is when the derivative, capital F prime, is increasing. And it's concave down if capital F prime is decreasing. So I can say F is concave up on, and the intervals where our graph is increasing would be from 0 to 1, and then also from 3 on, so 3 to infinity. And I'll just put the reason so we know, since capital F prime, which again is lowercase f because we have the graph of, is increasing. And then a similar reason for where it's decreasing, but it would just be the interval from 1 to 3. So f is concave down on 1 to 3, since capital F prime, which is lowercase f, is decreasing. And then C, at what values of x does capital F have an inflection point? 1 and 3. Because an inflection point, again, is where it changes concavity, so it's changing at 1 and then changing back at 3. So at x equals 1 and x equals 3. And this, again, this is so you, if you want to write this down so you understand why, since this is where f is changing concavity, so since f changes concavity at those values. And so this is even thinking ahead to if I'm grading this type of question on your test. If you had your intervals of concavity wrong, but your inflection points matched what you had for intervals of concavity, you wouldn't lose points for both. So typically when I grade this type of question, I'm looking at your intervals of concavity, and then if those are wrong, I look at those for how you answered where inflection points are to make sure that you're understanding that the inflection points would be where the change in concavity is. All right, and then D says now if capital F of 0 is 1, sketch the graph of F. So this means because the graph of lowercase f, which is the derivative of capital F, since it starts at the x value 0, this means our starting point has to be 0, 1. And we're sketching what the antiderivative might look like. So it's working backwards. You are given the graph of the derivative and you're trying to sketch the original function. Some of you have already tried to do this as you're answering questions. So, and you can use what you came up with. So I know my antiderivative that I'm going to draw is going to be increasing everywhere. But what I do need to pay attention to is the concavity as I'm drawing. So I know it's going to change concavity at 1 and at 3. So I need to start out from 0 to 1 with a curve that's increasing and concave up. Start like this. And then from 1 to 3, I'm still increasing, but the concavity changes to concave down. And then at 3, it's changing back to concave up, even though you're still increasing. It looks kind of weird, but that would be a possible graph. And then E asks how many antiderivatives F has. Well, you can take the antiderivative of any function. If it's a polynomial, it would keep going up a degree instead of going down. So any function will have an antiderivative. It does. Yes, that's the thing. So in D, we sketched the antiderivative that starts at 0, 1. But if this wasn't given to you, if this wasn't given to you, you may have all started your graph in a different spot. The shape should be the same. So it does have infinitely many antiderivatives. And again, this is really understanding the idea and the concept in this section. Actually finding antiderivatives we will do later. But this means I could have a different antiderivative. Say if I, instead of starting at 0, 1, say I start at 0, 2. But I still have the same shape. That's another antiderivative. I could start at 0, 3. I could start at 0, negative 1. So it's just shifting the graph. So ultimately, if you're asked to graph an antiderivative, where you graph it, I guess in terms of your y values, doesn't matter unless it specifies a point that it has to go through. That would be a specific or a particular antiderivative. If you have a polynomial, it'll go up a degree. Because the derivative will go down a degree. Antiderivative, you're going backwards, it would go up. Because think if you have f prime and it's a quadratic, then f would be cubic. It's going up a degree. The derivative would go down. That's for polynomials, that works, but other functions besides polynomials, they still have derivatives and antiderivatives. All right. So I do have, here's what I want you to do with some time that's remaining here. So one, there is some practice out of the book that you can look at. I'll go through any questions you have tomorrow. Even answers will be on Canvas. What I want you to do right now together in your groups, on the following page, and some of the questions that I have in the practice from the book go through these same ideas. So what's on the back side of the page you were just on, you are given for both, so 1 and 2 you're looking at the column. So 1 is the first column, 2 is the second column. And they're giving you at the top, the first graph is the graph of a function f. And below that graph are 3 other graphs in random order, the graphs of f prime, f double prime, and then a function capital F whose derivative is f, meaning it's the antiderivative. So for example, in number 1, you would look at these 3 graphs and identify which one is the graph of f prime, which is the graph of f double prime, and which is the graph of the antiderivative, and label them. You would do that for both 1 and 2. So I'd like you to talk about that in your groups, identify for both problems which is f prime, f double prime, and the antiderivative. And then the following page, because you can start on this as well, this is practice for you in graphing antiderivatives. So these graphs you are given are all graphs of the derivative f prime, and you are sketching the graph of f. So you are not graphing the derivative, you are graphing the antiderivative. Okay, and we've had some practice with that, not just today, but I know starting out 210, we actually had a graph of f prime and we graphed f. So you're thinking of the relationships, you're working backwards. So I just want to give you time to work through this and think through it while I walk around and answer individual questions. But I do have a key for any of these.